Let's talk about a simple TCAD solar cell example. Uh, these are the dimensions that'll be in the tutorial, but essentially we have an N-type region and a P-type region, and the doping variables are ND and NA. And then the width or the height of that region is set by DN for the N-type and DP for the P-type. The aluminum are just set to 1,000 angstroms or 0.1. You don't really control that. And the anti-reflective coating thickness that you set. These aren't necessarily drawn to scale, right? The width, W front, is how wide the aluminum front contact is. So if you made the aluminum front contact equal to the total width of the solar cell, no light would get in, which hopefully the simulation would show. Anyway, to see how that works in progress or in reality, let's go. So when you open up and save your file and start CentOS Workbench, which is a whole other, give some instructions, you'll see something like this. And here are all the variables. So I can just run, and you should see that it's because it's just drawing the picture, it's very quick. If I double click here, every file associated with that particular node comes up. The big one is underscore mesh TDR, and that will show you the device. And you can see the AR coating set to 0.1 micron, and the thickness of the aluminum set there as well. It's 0.1 micron. And if I zoom in, you should be able to see this purple shape, okay? And that means that the contact is there. And if you look at the bottom, you should be able to see that as well. And so if I turn everything else off, there's the top contact. Okay. And just double clicking again. There's an unzoom feature. You can see the top contact is where it's supposed to be, and the bottom contact is where it's supposed to be. When I turned off those layers, it got a little confusing. Now, if you want to see the code, it's all here. I've described it in another file, but I've written it all with variables so that you don't have to worry about it. Then we run sDevice, which is the simulation. We want to look at the code. This code is a lot to understand, let's just say. But basically it's setting up an IV simulation. Just start that while we're talking. And the way I've set the grids and things is that it's pretty safe. Now if I want to see what's going on that node, I double click it. And I did not save a TDR, but that's okay. So this file, if I put the anode out of voltage to the x-axis and the total current of the anode to the left axis, I get an IV curve. And you can see nothing, very small amount, an exponential region, and then a transition region to resistance. Right? So if I just make that logarithmic, you can see the area in which to extract your IS and N, and where to extract RS. That being said, we do that automatically. And then here is some code, which actually I'm going to run it first, then we can explore, where it turns the light on and runs the same voltage sweep. Rather than put the data here for the light spectrum, it just saves it. So if you copy this over, all of that should come. Right? And it's just, here's all the flags that are turned on. And the important thing is that it's an optical simulation, so we have to add this to the file. And it's done. So if I double click on that, this one we did save the TDR. You can see some interesting things where absorbed photon density, right? The aluminum shadowed it. Absorption heat spectrum. That's our generation spectrum. And we can also look at the current voltage relationship. You can see we have a negative current and that it passes 0 a little bit above 0.4 volts. And now if we run inspect, rather than edit the code, gives us our ideality factor, our IS, RS, short circuit current, open circuit voltage, the current that gives you the maximum power, fill factor, and the voltage at the maximum power. If you were to edit that code, it doesn't hide the things like Python. It's Tickle, and you have to write your own numerical solving routines. Now, just a quick thing on how to use this. I'm just going to first show you that if you want to get rid of all this, you can go to Operations Cleanup, and it gets rid of your thing. Now, if I want to do an experiment like, I don't know, let's change the oxide thickness. I can add parameters values to TOX. I can have a list of values. I can have a linear set here. So let's put 0.01, 0.1, number of values, 10. I think if I put step, let's just see. Okay. So my 0.1 is still there. I get rid of that. actually, let's make it 0.05. Now I should have to do is save the project, operations run. Interestingly, it choked on the first value, but the other ones are running. Then you probably noticed at home that there was 2 decimal points there. It's the issue. So if I do edit value, right click, edit, get rid of that. So this will take some time to run. What it will do is spit out all those variables, which you can kind of just cut and paste into Excel. Like here's the experiment. You can cut and paste that to, or since it's on Unix, you can cut and paste it into a Google Sheet for Excel manipulation later, and then you could plot out the extracted variables. This is going fairly quick, but I think a video of me watching a simulation, not too helpful. So we'll leave it there for now. Or you know what? I'll just pause. How about that? Ready? So the experiment ran, and of course we only changed this oxide thickness, and so the ends don't change, IS, RS. The short circuit current and the open circuit voltage, nothing else changed. And the reason is that this that AR coating just is not thick enough. It didn't really change it enough. Um, let's see if we can do edit values. So let's try 0.09, 0.1, 3. And see if we can see some better results. Oh, that's not good. Luckily, I have a backup. Anyway, optimizing that will be another video.